Hello there, my name is Pedro, and today we're going to talk about porting applications to ARM64 Windows. Porting applications to a new platform is a journey that starts with the operating system, the documentation, software kits, compiler. But while some new tech enthusiasts can't wait to jump into a new architecture, most developers must prioritize time and investment and wait for the platform to prove themselves viable before porting. Of course, one part of becoming viable is having apps running in it to begin with. One common way to break this chicken and egg cycle is for the platform to provide some sort of emulation compatibility layer which enables applications written for another platform to run. For example, Windows on ARM64 supports applications written for Windows ARM32, Windows x86 both 32 and 64 bits, as well as ARM64 Linux. While these compatibility layers certainly accelerate adoption, they might also inhibit porting. If devs find their app to run well enough under emulation, why would they port? Compat layers imply varying levels of overhead. This means that a platform will truly shine and be competitive once most applications are running natively with optimal performance and battery life. This made us at Microsoft reflect how we could make emulation an ally and a catalyst of an application porting instead of an inhibitor. Porting applications is a complex operation. We have to understand that because mostly it's an all or nothing operation. All components and dependencies must be ported in order for the application to run. This was the law that we set ourselves to break with ARM64EC. ARM64EC is native, as it runs natively on the CPU, but it is compatible with x64. And by compatible, I mean we can link them together, statically and dynamically. We can mix emulated and native code together in the same application, even in the same binary. ARM64EC provides the opportunity to port the applications piece by piece. That makes the nativeness of an application rather a grayscale instead of a black and white picture. You can start with a fully emulated app and then incrementally port portions of the code to ARM64EC one at a time, over time, improving the performance and the battery life as you go. The key here is that having that flexibility to make progress and focus your efforts in the places where you can most improve the application's experience. Start with code that is performance sensitive or easy to port. Leave the harder code like x64 assembly for a second pass. And also leave dependencies that you have little control over as x64 code until they can be ported to ARM64 as well. This gives you also the possibility to be compatible with third-party plugins if you have a third-party plugin ecosystem. And this is essentially for some apps. The 64-bit Office in ARM64 is compiled for ARM64EC precisely so that it can load pre-existing plugins written for the x64 platform. When dealing with dependencies, there is an important picture to retain. We know that ARM64 classic or original code and x64 code can't be linked together. That's the problem we're trying to solve. And we know that ARM64EC and x64 code can be linked together. That's the point of ARM64EC. But by association, we can already see what's going to happen. ARM64EC and the original ARM64 ABIs are not compatible and cannot link together. ARM64EC can link to ARM64EC and to x64 code, but not original ARM64. This is important. So how do you get started on ARM64EC? Well, the tools are already available. They're in production. They're included with Visual Studio 2022 version 17.3. You just have to install the tools. And then after the tools are installed, All you have to do is open your solution project and add the Arm64EC configuration just as you would do for any new platform. The original thing here is that not all projects within the solution must be changed to target Arm64EC. As we saw, you can leave portions targeting x64 instead and tackle those later. Fundamentally, Arm64EC is interoperable with x64. It is designed to be totally transparent to the user and to the developer. The operating system handles engaging and disengaging the emulator at the right time when the execution is transferred from one to the other. Apps run faster when executing Arm64EC code, but they transition back and forth so smoothly. For this to be possible, not only the calling conventions must match between x64 and Arm64EC, but also the data type definitions, such as structures in your code. That means that preprocessor definitions counterintuitively will match the x64 values. However, there is a dedicated Arm64EC defined that can be used if you're writing code specifically for Arm64EC. If Arm64EC follows the x64 path, then what happens if your code uses x64 compiler intrinsic functions? To make the transition from x64 to EC easier, the SDK automatically translates any x64 intrinsics to Arm64EC portable code. Just include the intrin.h, which you already do probably. This gets you up and running with Arm64EC easily. It will work. But you could still optimize that later to get better performance by using the Arm64 intrinsic functions instead of x64 one. You can use Arm64EC preprocessor we saw before to add Arm64 intrinsics in the EC case. You can see a simplified example of this technique here, where you already converted a chunk of SSE code to Neon, and that applies to both your Arm64 original and your EC configuration. Now let's see how this all fits together. Here, I have the popular Notepad++ source project open in Visual Studio 2022. Now, Notepad++ already supports being compiled as Arm64, but I added the Arm64EC configuration to this project. It has 3 sub-projects, and I've converted all of them to EC, but as we saw before, I could have left one or more as x64 if I needed to. To see what's going on, let's run it under the debugger. I've left a breakpoint in the About box, so let's trigger that breakpoint. Now, because Notepad++ was compiled for Arm64EC, it is actually ARM code, which is running natively in the CPU. No emulation is taking place. The operating system binaries, of course, are also native ARM binaries. So what is the advantage of compiling Notepad++ as Arm64EC? Well, Notepad++ supports plugins. And if I had compiled Notepad++ as Arm64, I needed to recompile all plugins as Arm64 as well. But compiling as Arm64EC makes it compatible with a very rich existing ecosystem of x64 plugins. And that's exactly what I did. I downloaded a plugin called preview.html from the internet. I don't have the source code for it. I just have the binary distribution for x64. And I put the plugin inside of the plugins folder of Notepad++. As we can see, Preview HTML loaded, and it's working inside of Notepad++, even though it is a pre-existing unmodified x64 binary. So let's look at this once more inside of the debugger. Let's break in and look at the call stack. Now, at some point, Notepad++ code, plugin manager, called into the plugin. This function pointer is in preview.html, which must be x64 code, since the binary is all x64 code. Let's look at that by switching to disassembly and looking at the first frame of preview HTML. Yes, we can see that it is x64 code and is running under the emulator. The opposite operation happens when preview HTML, x64 code, calls into the operating system. Because the operating system's binaries, or back into Notepad++, of course, because they are Arm64EC code that can run natively in the CPU, the emulator stops and the code starts running natively. So we have interoperability with x64 code, but we run natively when we can recompile the code. Now let me hand it off to Koki, who will cover a very interesting case study on this.
Thanks, Pedro. I'm Koki, a staff engineer at Arm. From my side, I'll share some experimental results with Arm64EC. I've tested OpenCV library, which is well-known computer vision library. Its source code is cross-platform, and then it can be built with Visual Studio for Windows. If you open OpenCV source code with Visual Studio, you can see that it contains a lot of projects in one solution, and it generates many library files and executables. This diagram briefly describes the OpenCV source code structure. Projects in Visual Studio are corresponding to these boxes. As explained, developers can choose to compile with Arm64EC or x64 project by project basis. In order to see the results of effect of Arm64EC, I have divided these projects into 6 layers. This separation allows partial porting without breaking dependencies between them. For example, the most lower layers includes third-party libraries, and the core layer defines the basic OpenCV types that uses the libraries. And then the upper image processing layer defines the processing core. And the layer 3 includes middleware such as video and the image codecs. Layer 2 includes high-level functionality such as feature extraction or object detection or something like that. And then the layer 1 includes the most upper layer that tests these high-level functionalities. I have prepared 8 types of program binaries to run and then compared their execution performance. The first one is an x64 binary, which is built by taking all the code and then compiling them with x64. It runs entirely under emulation. Next is an Arm64EC binary, level 1. The level indicates how much layers are ported to Arm64EC. It means that, for example, for level 1, I took only layer 1 code and then compile it with Arm64EC, and the rest of the code is compiled with x64. In this case, only layer 1 runs natively, and then the rest of the code runs under emulation. In this way, I prepared Arm64EC binaries from level 1 to 6, depending on how much they are ported. Finally, I also prepared Arm64 binary. I took all the code and then compiled it as previously Arm64. This is the experiment setting. For this testing, I chose 3 tests from the layer 1. I picked up classical key point detection for still images, optical flow for video processing, and object detection as neural network model processing. On the horizontal axis of this graph, I list those 3 tests. In one test, each color bar corresponds to the 8 binaries I explained in the previous page, indicating how much layers has been ported to Arm native code. The vertical axis shows execution time, which is a ratio of the execution time compared to x64 emulation, meaning the lower the number, the faster the execution speed. The lightest blue is the x64 emulation. This means that it is always 100%. The darker the color, the greater the ratio of ARM native code in the binary. The darkest blue is for Arm64 native build. This figure shows that more you port your code to Arm64EC, the faster it gets. If you look at the bar charts of features to the orb, which is key point detection, you can see that changing from level 1 to level 2 porting, the second and the third bar from the left did improve dramatically the execution time here. Level 2 to level 6 doesn't change much, and then they are close to Arm64 native performance. You can also see the similar trend from the rest of the graph. From this, we can see that which layers are performance critical modules. Probably you don't need to port the rest of the code anymore because it's not effective and it does not contribute much to speeding up. So with Arm64EC, you can determine which parts are most effective for porting, and then you can focus your efforts there. So that's the main advantage of Arm64EC. If you are interested in knowing more about this experiment setting and the results, I explain them a little bit more in detail in a separate talk. Please search for another Arm64EC talk in Dev Summit. Now hand back to Pedro. Thank you.
Thank you, Koki. That was a great example. And thank you everyone for attending this presentation. I hope you found the content and the technology valuable. If you did, I would encourage you to access aka.ms/Windows 11 on ARM for additional material on the subject, both on the toolchain and on the Arm64EC ABI. See you next time.